Alright. So let's continue analyzing that equation we worked on yesterday. So we're dealing with vinegar or acetic acid. It's usually written as CH3COOH with the H coming after. Yesterday I wrote it with it before, but this is the usual way you see it. We calculated its molar mass, 60.05196 grams per mole. Looking up some other information on it, 1.053 grams per cubic centimeter. What is this value? And what does this whole number represent? And what is that? A unit of? What is grams a unit of? Mass, not weight. So mass, and what's cubic centimeter? Volume. So what's mass per volume? Density. Also written as 0.053. What's another unit for cubic centimeters? Milliliters. So I have found in the lab, I don't know how old it is and if it's decomposed some, but it claims it's 5% vinegar. But in the equation, we're dealing with grams and moles. We have 1 mole to 1 mole, or 1 molecule to 1 molecule. So we need to figure out the molarity of this. So what is the molarity for 5% vinegar? Do you remember what molarity is? Molarity is defined as the moles of solute. It's the thing you're dissolving. Per volume of solution. And the volume is going to be in liters. Yeah, we covered these. So, molarity is constant after you made it. It doesn't matter if you have a 1 molar, if you have a concentration of 1 molar, then 1 drop of it is 1 molar, or 1 gallon of it's 1 molar. It's constant, it doesn't change. It's like density. So I like just choosing a starting like with 100 milliliters. Let's just guesstimate. Because we know it doesn't matter if it's 1 milliliter, 100 milliliters, or 1 billion milliliters. It would all have the same molarity. But here we get an issue of ambiguity. What does 5% mean? There are 2 types of concentrations. There is, usually you'll see this written on it. I don't like the bottom one. It should be M/, but they use that. This is volume per volume. And this would be weight per volume. Which again, I don't like this one, as it's really mass, but as long as you don't plan on going anywhere else in the universe and stay on Earth, weight doesn't change on Earth too much. But there's 2 ways we could have done this. It could be 5% by mass or 5% by volume. So you can have a percent by volume, or you can have a percent by mass. Sometimes these work out the same. That's assuming that the density is close to the density of the liquid you're putting it in. And what's the density of water? Exactly one. 1 gram per milliliter. That's how we uh, that's how we initially defined the gram, I think. But these two numbers are very similar. It's basically has the same density as water. So whether or not it was volume by percent by volume or percent by mass, either one of these, it doesn't. It's basically approximately the same result. The example I use in IPC is, let's say that I had a giant metal block that had a volume of 1 milliliter, but a mass of 10 grams. And I put onto it a drop of water that has a volume of 1 milliliter and a mass of 1 gram, because the density is 1 gram. So by volume, this would be by the percent by volume. Together, it's 2 milliliters total volume. And then we have what percentage of this is metal. So it's one milliliter is metal, and 2 milliliters is the total. So altogether, it's 50% metal, right? However, if I did this by mass, I would get, yes. So it would be 11 grams would be your total, and 1 gram, and no, it would be this. It would be 10 grams per 11 grams, which is odd because of the volume error. Maybe it's weight per weight is what I could be confused on this. Anyway, you get over 90.1% metal. My point, regardless, is to show you that whether or not you do by mass or by volume, I think this has to be weight per weight. But I've seen weight per volume ratio, and I'm confused on that. This should be weight per weight for concentration. But my point is just to show you that these numbers can be drastically different. But in this case, it doesn't matter, as the density is the same for both of them. So, I'll go later on and do an example where I'm showing these where you have to know density. But for right now, we don't need to concern ourselves. We're going to assume they're equal density or density. So if we have 100 milliliters of vinegar, then I'm going to assume that this is volume divided by volume. So that means we have 5 milliliters of vinegar per 100 milliliter solution to give us the 5%. And you're supposed to take the density into effect here. I'm going to do that. So converting 5 milliliters into grams. So I need to cancel out milliliters, so I multiply it by 0.05 grams per milliliter, 1 milliliter. Milliliters cancel out. And I get, in my example, 5.265 grams of vinegar per 100 milliliters. And again, 100 milliliters is just a made-up number for analysis. You could use any starting. You could start with a liter, and it's actually probably would have worked out better to start with a liter. Now I'm thinking of it about like 100 milliliters. So we're trying to find molarity, so we need moles per volume. Now we need to convert the grams into moles. So the molarity is, the molar mass is 60.05196 grams per 1 mole. Grams cancel out, giving us moles. Ooh, and I got a way different value. I got 0.08764 moles. I thought this would actually get me a more accurate number, but this gave me a much worse number than the previous class. And I'll discuss what I did in the previous class in a second. So now I have the number of moles. And this is per 100 milliliters. So it's almost molarity. The thing is, molarity is always defined in liters. So 100 milliliters is how many liters? 100 milliliters is how many liters? A million, milli means a thousandth. 0.1 liters. So if I take my moles and divide by 0.1 liters, I get 0.087674 moles divided by 0.1 liters gives me a molarity of 0.87674 mole per liter, which we usually just abbreviate as a capital M. Looking up online, the answer I get is 0.83 M carried is the official molarity for theoretical 5% yield. And in the other class, I didn't use density. So here I went ahead and used density to get this number. I just assumed that it is 5 milliliters vinegar is equal to 5 grams vinegar. Which, yeah, I didn't make a mistake. And whenever I did that and did this calculation using 5 grams here instead of 5.26, I ended up getting a molarity of 0.08326 grams, which makes me think this should be, I did something wrong, because this is more accurate. I'll reanalyze this tomorrow. I thought using density for this class would give me a more precise number, because I'm trying to get to exactly 0.83 carried. I will look at this later, but we'll go ahead and use this number, the one I googled for 5%, as it worked out pretty well last class when we did this experiment. I will look at why. Alright, so basically we have 0.83 carried molar vinegar is equivalent to 5% vinegar. I'm going to keep Googling and see if I can get a different value. So, molarity of 5% vinegar. Yeah, I'm seeing 833. 0.833 molarity. Vinegar is equivalent to 5% vinegar. Yeah, so what they did, I'm looking it up. So the 5% vinegar is assuming percent by mass. So it's 5 grams. 5 grams of vinegar exactly per 5 or per 100 milliliters. So it's weight per volume. And this calculation here was assuming volume by volume. And like I was saying, depending on which one you assume is it, you get different numbers. And usually on the bottom it will say. So this was assuming weight per volume is the percentage. This was assuming volume per volume was the percentage. While this value is assuming weight per volume. And we'll go with that because I think that's what it is. Alright. But we have the molarity. The molarity is going to be this. This is done if we use weight per volume. I'm going to look at the bottom too. So, I was going to use 10 grams. I'll still go through the analysis because this is going to be useful. Let's assume that we use 10 grams of sodium bicarbonate. The question is how much 5% vinegar is needed to fully react with the 10 grams of sodium bicarbonate. He still hasn't showed up. Alright. Alright, bye. So, how will we solve this? So this is sodium bicarbonate. Its molarity is 84.007 grams per mole. So remember the equation, we have vinegar with baking soda, and it's a 1 mole to 1 mole reaction. The coefficients is 1. We can't really deal with grams when working on this. We always need to temporarily convert to moles. So we're given 10 grams, that's not a good number to start with. We need to convert it into moles. So the molarity of sodium bicarbonate is 84.007 grams per 1 mole. Grams cancel out, giving us 0.1190377 moles of sodium bicarbonate. And we know it's a 1-to-1 ratio. If we had 2 moles of baking soda, we need to use 2 moles of vinegar. If we have 0.1190377 moles of sodium bicarbonate, we need 0.1190377 moles of vinegar. And we have a ratio now. The molarity is the ratio that converts between moles and liters. So we take this number, and this is where dimensional analysis really is needed, as it's going to be constantly dimensional analysis when working this out. So we have moles. Molarity is 0.8 0.33 moles per 1 liter. Moles cancel out and gives us liters. So doing that equation, we get 0.1429 liters. And to make it better, we're going to just turn it into milliliters. So roughly 143 milliliters. So to counteract 10 grams of sodium bicarbonate, we need 143 milliliters of 5% vinegar. Make sense? So let's go in the lab and do this. However, we're not going to be doing 10 grams. We're going to do roughly 5 grams, but it'll scale. So if we have 10 grams of baking soda, we need 143 milliliters of vinegar. If we use 5 grams of this, then we just half this. Make sense?